It gives me immense pleasure and joy to come here for the course Aircraft Stability and Control. Today is my lecture number 11. In this, I am going to discuss about longitudinal control. You know that I am Dr. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In today's lecture, I am going to cover these topics, starting with axis of rotation and experiments on longitudinal stability, trim point, role of elevator to trim the aircraft at particular coefficient of lift, change in lift due to elevator deflection, change in angle of attack seen by tail due to elevator deflection, change in moment due to elevator deflection. In this lecture, I am going to reply the questions which are: what is the role of elevator in aircraft longitudinal stability? Does elevator change moment or lift or both? Very important thing. In this lecture, we are going to discuss about longitudinal control. Once I talk about the longitudinal, so first I have to describe what is the longitudinal. If you see this aircraft, here we have the axis which is passing from nose to tail. This axis which is passing from nose to tail via center of gravity, this is called the longitudinal axis. Another axis which is passing from wingtip to wingtip via center of gravity, it is called the lateral axis. And one axis which is passing from center of gravity vertically like this is called vertical axis or yaw axis. From the last 10 classes, I am only discussing about longitudinal stability, and further some 10 more classes or 9 classes I will be discussing only about longitudinal stability, because longitudinal stability has to play a more role comparing to other two stability, that is lateral stability and this directional stability. Till now, I have discussed about basics of stability, types of stability, that is static stability and the dynamic stability, types of motions. I have described about the 6 motions. Out of that, only 2 motions are this longitudinal dynamic stable, and 4 motions are statically stable. Out of 6, only 2 motions are dynamic stable. And so we have to understand that we all are working for dynamic stability, but the one condition and basic precondition to have a dynamic stability, that any aircraft should be statically stable. As of now, I have discussed about contribution of wing, contribution of tail, neutral point, static margin, and these all things are related with longitudinal stability. Means the motion when it happened in the longitudinal axis. So once I talk about longitudinal, it means the pitching. Pitching happens in the lateral axis. So with respect to the lateral axis, the motion pitch up and the pitch down, this motion is called the longitudinal motion, and the control which is related with this longitudinal stability is the elevator. This you can see here black, this is the black ink, this black painted, this is the elevator, and once we deflect this elevator, there is going to be some changes in aircraft stability. And also once I talk about the control, we have the 3 typical control of the aircraft. One is elevator, which is making pitch up or the pitch down. Another is aileron. Ailerons are fitted at the wing tip, both sides, and they are operated in differential form. If one will go up, another will go down. So in this way, the work of aileron is to give the roll. Just I want to explain here that if I want to roll the aircraft left wing down, it means I have to have more lift on the right wing and less lift on the left wing. So I have to increase this aileron. The right aileron should go down and left aileron should go up. So if it is going down, the lift will be more in this right wing, and left will be less, and it will rotate or this left wing will go down and right will go up. So this is the purpose of ailerons. If I want to make nose up and down, it is called yawing motion. So if I want to make nose up and down, this left or right, that time I have to use the rudder. Rudders are fixed behind the vertical fin. So if I want to make nose left, so I have to move this thing left so that the force will be generated in this direction, like this, like this, like this, and aircraft nose will go left. If I want to make nose right, then this has to go right. The rudder will move in this direction. A force will be generated in this direction and it will move like this. So this is called side force. So aircraft is in 6 degrees of motion. In this we have 3 forces. One is the vertical forces, another is horizontal forces, one is this sidewise forces, and we have the 3 rotations. One is pitching with respect to the lateral axis, another is rolling with respect to the longitudinal axis, and last one but not the least is yawing, which is with respect to the vertical axis. So these are the just introduction of this lecture, and I am going to further about, I have discussed about the Mann Ki Baat. So in Mann Ki Baat, I want to say that the aircraft is, we have seen that aircraft and the contribution of wing, and we have seen that the wing contribution is normally, this is the CG and here is the AC. So this is the like this. So the wing contribution is that this is the Cm naught and this is the alpha. So wing contribution is Cm naught is greater than 0 and Cm alpha is also greater than 0. So it is, the wing contribution is like this. However, we don't want like this. We want that our Cm versus alpha plot should go like this. So there should be a trim point and this Cm alpha should be less than 0, or we can say negative, and Cm naught should be positive. This is our requirement. This dotted line is our requirement. To have this thing, we have seen that if this is the wing, we need to make a tail. This is the tail and this is the wing, and here it is in this direction, Cm AC wing in this direction, and so we want a lift in this direction. This is called CLT. It should be in this direction, and this is called CMT. So this should be Cm alpha of the wing should be, and the sum of Cm alpha of the tail should be 0 to balance the aircraft. This we have discussed. Now we have to see about the control. So in the horizontal tail, we are putting a elevator, and this elevator is known as a delta E, and delta E is a deflection of the elevator, and if it is downward it is a positive, and if it is upward it is a negative. So we are going to discuss in this class what is the effect of control, and when we talk about the control, here we are talking about longitudinal control. So in the longitudinal control, the effect of elevator has to be considered, and this we are going to discuss in this class. So here just I want to discuss about axis of the rotation, and here I have shown you that this is horizontal line. This from tail to nose or nose to tail, it is called the longitudinal axis, which is used for rolling purpose. From aircraft wingtip to aircraft wingtip via the center of gravity, here is the center of gravity, and it is giving the roll this lateral axis, and in this lateral axis pitch taking place, and the third axis is a vertical axis. In this, nose will go left or right, and it is called the yawing axis. So axis as applied to aviation is defined an imaginary line about which a body rotates. I want to discuss in this an aircraft in flight maneuver in 3 dimensions. To control this moment, the pilot manipulates the flight control to cause the aircraft to rotate about one or more of its 3 axis rotation. These 3 axes referred to as a longitudinal axis, lateral axis, and vertical axis are each perpendicular to the others and intersects at the aircraft center of gravity. Here we can see that as I want to express here something, a new concept, and here aircraft longitudinal control experiment. We can do some experiment in our wind tunnel, which is available in our Institute of Aeronautical Engineering Aerodynamics Lab. We have the wind tunnel with 600 millimeter by 600 millimeter by 2000 millimeter of cross section with the highest speed of 50 meter per second. We have the 6 component balance. We have 32 manometer. We have boundary layer measurement. We have vortex measurement. We have static pressure and different pressure measurement techniques. These all systems are available with our wind tunnel. So here, just I want to explain that here how to find out the Cm alpha. Cm alpha, it is a coefficient of moment and the variation of alpha, and here is CL alpha, xCg by C bar minus xAc by C bar minus neta VHCl alpha T into 1 minus d epsilon by d alpha. Here, this you can see, I have mentioned here 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 is a fan. The fan is used to give the here blow to the aircraft. Then we have the wing. Number 2 is a wing, and this number 3 is a fuselage or airframe. Number 4 is a tail. Number 5 is elevator. So this number 5 is elevator. Number 6 is rate gyro. We have to put here a rate gyro, which will give all the motions and acceleration and the rotation of the aircraft. Then we have the servo motor. This is the same one which is used to deflect this system. Then we have the DAC system 8, and then we have 9, one small computer here. In this computer we are fixing this item and we are getting the necessary output. So a very simple system I have shown here, and this I have taken from one of the research. I could not put the source here. Okay, so in this way we can find the control and the effect of the especially elevator control or the longitudinal control of the aircraft. Now I am going to discuss about longitudinal control. So let's say aircraft is cruising in trim point. if we talk about the trim point, so here is the one aircraft, and if I talk about the trim point, so in trim point this lift is equal to weight, and this is the thrust is equal to drag, and here this is the trim point, here it is mentioned. Let's say CL increases to 0.2. Now we are here, and due to some gust or something, this CL is increased from 1 to, it was 1 and now it has reached to the 0.2. So if we take from here and parallel to this, because we want the same slope, so we need here, this is the positive delta Cm naught. We need this much increase of CL will be there. So let's say that V1 is equal to producing the CL1, and in this case lift is equal to weight. Another case, when V2 is equal to, it is producing the CL2. Here CL1 is greater than CL2. If V2 is greater than V1, if V2 is greater than V1, then trim point 2.2 negative moment is required, is as same, is created, and to nullify the positive moment needed. So in this case we have to make elevator up. Okay, so if we make the elevator up, this will make like this, and in this way your aircraft will be neutralized. Thus delta Cm is generated by the elevator, and this deflection is called delta E trim. So if you see here at this point, this is called the delta E trim. Here delta E trim at the new point required. How much delta E trim is required? So mostly the elevator are moving from plus minus 15 to plus minus 20 degrees only applicable. Let us start mathematical formulations of the wing. If you make the more angle of attack, wing will stall. So elevator also has a limit, and that is up to plus minus 15 degree to plus minus 20 degree angle of attack of deflection E is needed. So we have to now derive the equation for the CL delta E, that is also called the control power of the elevator. So we know that CL, the coefficient of lift, is equal to, is a function of alpha angle of attack and delta E. CL is a function of also as alpha and delta E. By the Taylor series, if we expand it, this CL is equal to CL naught plus CL alpha into alpha plus CL delta E into delta E. Here CL alpha is dCl by d alpha when delta E is constant. So here the CL alpha is what? It is a dCl by dl alpha when we make this term as a constant. But if you want this CL delta E, it is a dCl by delta E when this dCl by d alpha is 0 or constant. So in this way, so modeling in wind tunnel. So how, if you want make the aircraft model in wind tunnel, how we can perform this experiment in wind tunnel. So if you see here, this is the aircraft and the flow is coming from this side. First case, we will see that the elevator is fixed, it is not moving. Only angle of attack, it is aircraft angle of attack alpha is moving. As alpha is moving, the lift will move and the CL of this aircraft will change accordingly. So in this case, CL alpha into alpha we will consider, and this will be in a partial differential. Another parameters we make constant. Second case, we will make alpha constant, but we will move the elevator up or down like this. So if we move this alpha or this delta E, this deflection of the elevator plus and minus, and wind tunnel, we are observing how much CL variation is taking place by variation of the delta E or the deflection of the elevator. So now we will see that. Let us have closer look of CL delta E. How to get CL delta E? So we know that lift at the tail, delta LT is equal to half rho V square T. ST is the area of the tail and CLT. Rho is a density, V is a velocity. Now, this delta CLT, we have to divide this thing by half rho V square infinity. Okay, so infinity or the wing. So here ST by this S, ST by S and CL alpha T. And we know that half rho V square and half rho V square is a neta. And here ST by S into CLT. So we got the equation for coefficient of lift of the tail, and this equation is neta ST by S CL alpha T. Now this delta CL is equal to neta ST by S. For CLT we can write dCLT by d delta alpha. Now we are changing the deflection of elevator. So now dCLT by d delta E into delta E. So now this dCLT by d delta E is equal to dCLT by d alpha T into d alpha T by d delta E. So this alpha and alpha cancel. So here you will get dCLT is equal to CL alpha T into this will become tau. And this tau is the ratio of difference between alpha T and the delta E. And this is called the tau, and this tau is a performance characteristics of the elevator deflection. So here we got that dCL T by d delta E is equal to CL alpha T into tau. Now what is tau? The tau is called the flap effectiveness or elevator effectiveness parameter. Value we can get by the graph. This we can see here that this is the plot of tau versus SE by ST, and if this is SE by ST always less than 1, and mostly it is between 0.4 to 0.5. And if you see, this is the plot, and as per this plot, if we put a horizontal line, so if we will get 0.5, 0.6, 0.8. So this ranges from 0.5 to 0.8. This tau value will range in this, and SE by ST will range from 0.5 to 0.4 to 0.5. So as per that, we have to calculate by this plot. And what is this SE by ST? So if you take, this is the total area of the tail including elevator. This is called elevator area. This is called the tail area. And in this, if you from the hinge line, you put like this, and this area which is I am hatching here, this area is called SE, area of elevator. So this SE by ST is equal to elevator area and tail area, and this tau is 0.4 to 0.5. So dCLT by d alpha T is a geometrical parameter. So if you see here, all here geometrical parameters are coming. The size of this elevator is depend, and in this only this control power, this dCl by d delta is matters. So now here delta CL is equal to ST by S neta delta CLT. So here ST by S neta CL alpha T into tau into delta E. So now CL delta E is equal to ST by S neta CL alpha T into tau. So this we got. Now you know how to calculate change in CL because change in delta E. If CL delta E is positive, so the direction of this thing will be like this. So if the CL delta is positive, then tail will produce a anti-clockwise motion. Now delta Cm is delta CL gives a negative pitching moment. Just this delta CL, which is generated by delta E deflection here, this will give a negative pitching moment as shown here. So delta Cm by delta E. If you draw a plot between Cm and delta E, elevator gives CL delta E and then delta Cm is generated. So we get CL delta E is equal to neta ST by S CL alpha T into tau. If you see here that this is the Cm initially, and if you deflect the elevator and it will come to point 2, this lift will be increased and this much delta Cm. This is the increase in Cm due to delta E deflection, and it is a Cm naught, it is giving positive. So this Cm naught is making a more alpha variation, so more angle of attack, and this it will happen by deflecting downward. If you deflect the downward, the CL will be positive, and this CL positive will give negative pitching moment. Means nose down it will make. So now I want to calculate the delta Cm, and this delta Cm is equal to delta CL into LT. So minus, we have put the minus because direction of this thing is anti-clockwise direction. So neta ST by S CL alpha T tau into delta E into LT by C bar. In this case, this LT is tail arm moment and C bar is a average chord of the wing. So here Cm delta E is equal to dCm by delta E. So here this delta E will be cancelled. So minus ST by S LT by C into CL alpha T into tau. So here this will be minus neta VH CL alpha T into tau, and this delta E will be cancelled in the previous equation. So now Cm delta E is equal to minus neta VH CL alpha T into tau. So this is the equation for the Cm delta E. Cm delta E is called the elevator control power. Cm delta E can be increased with VH. So how do we increase this control power? By this VH or by the tau. So if we increase the size of the VH, means either the area of the horizontal tail or the LT, means the moment arm, if we increase, the value of Cm delta E will increase, and Cm delta E should be negative, and normally it is minus 0.8 to minus 1.5. CL delta E is positive and it is 0.5 to 0.7. This value we should understand. So now discussion on Cm delta E. The positive deflection of the elevator as shown here. positive deflection of the elevator. This is plus delta E. I can show here that this is the plus delta E floating down. Means downward moment will give delta CL upward. It is shown here. It is showing upward, which will generate a pitching moment negative in this direction as shown here. It is a negative pitching moment. So now here delta Cm due to delta CL is negative pitching moment. So here we got that delta Cm by delta E per unit change in elevator deflection. How much pitching moment is needed. So this is the meaning of Cm delta E. Means how much if you deflect per unit elevator, how much pitching moment you are getting. So we can get, if I increase the delta Cm nose up, the elevator to go up. So it is shown here. So in this case, the direction is opposite, and so let us see about pitching moment Cm delta E effect. So this you can see here at this is the trim condition, it is CL. As you go to more positive, this is the positive delta E, then what will happen? The positive CL will increase and this Cm will be more positive. And if you decrease upward, so your Cm will be decreased. So this is the importance of deflection of elevators in the aircraft. We are looking for Cm delta E. We will see it in elevator deflection. I know that CL delta E is equal to neta St by S CL alpha T into tau, and delta Cm is a negative minus neta St by S CL alpha T into tau into delta E into LT by C bar. So here this all LT is given, all the parameters are shown here. So if I make Cm delta E, means delta Cm by delta E, so this delta E will vanish. So here I will get minus n St by S CL, this LT by C CL alpha T into tau. So Cm delta elevator control power, Cm delta E is equal to minus neta VH CL alpha T into tau. So here VH is a tail volume ratio, tau is a performance parameter, that is delta alpha by delta E. So going to Cm delta E negative, if delta E is a positive, downwards will give a negative pitching moment that is stable, and if it is opposite, it will give a positive moment. In our next topic, I am going to discuss about calculation of trim angle, calculation of elevator deflection. What do you mean by trim condition? How does elevator help in attaining trim condition? These points I am going to discuss in my next topic, and hope this will be very useful for the next development of knowledge. This is my reference I have taken from NPTEL lecture of aircraft stability and control by Professor A.K. Ghosh, IIT Kanpur, and this is the link for the lecture. Any questions, you are welcome to ask me in this email, that is yagyadatta.dwivedhi@ire.ac.in, and you are welcome to ask any question in this mail. Thank you very much for the joining, and be tuned for my next lecture, and this lecture will be also very interesting to understanding about elevator and its effect on the stability and control of the aircraft. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.